See, let's continue our class, more particularly photochemistry, uh, organic photochemistry. Previously, we discussed about the photosensitization and a few examples of photosensitizers and more particularly a photochemistry of carbonyl compounds. Suppose a carbonyl compound is having ortho substitution. That means ortho substituted protons. If it contains a carbonyl compound, then such compounds undergo photoenol as the product, not the photoreduction. So here, a deuterated alpha substituted deuterated is the example how a photoenol is formed. So here I'm taking the ortho tertiary butyl one. Ortho tertiary butyl one means here there are no ortho substituted protons of carbonyl compound. And this kind of molecules undergo photoreduction. So photoreduction means a carbonyl compound is converted into alcohol. In addition to that, pinacol products also form. In addition to pinacol and photoreducted carbonyl compound, mixed pinacol also, also the products are formed. So here, in place of tertiary butanol, if we are taking a carbon ortho-substituted trifluorocarbon, this also gives a photoreduction product in addition to the pinacol one. With this, I will go to the next slide. In the next slide, one minute. Okay, I think it's struck. Slides are not moving. I will stop sharing and then I will go for a sharing again. So that we'll see. Stop sharing. Okay. Now I will share it again. Okay. Right. So okay. So now let us go to the next slide. The next slide. Okay. The next slide, I'm taking the view. Suppose a substituted carbonyl compound. Here is the substituted carbonyl compound. One is ortho-amino substituted and para-amino substituted benzophene. So these compounds suppress the photoreduction because of the electron donating nature of the amino group. What it makes that a carbonyl character reduces. That means carbonyl character reduces and forms a enol one, enol kind of moiety. That's the reason these ortho and para substituted amino suppress the photoreduction, more particularly in the polar solvents. Whereas the non-polar solvent, there is no such reduction of carbonyl character. Here, I'm taking one more hydroxy at ortho position and para positions. This Yes, Sujit, any questions? Okay. Hydroxy at ortho and hydroxy at para positions undergo photoreductions. I will go to the next slide. So in this one, here I am showing the enal character in presence of solvent. That means resonance 2. In polar solvent, resonance 2 will be the major one. That means it suppresses the carbonyl nature of the carbonyl compounds. That's the reason photoreduction suppresses. In nonpolar solvents, there is no carbonyl character is retained. Carbonyl character is retained. That's the reason there is no suppression of photo reduction. Then I will go to the next slide. In the next slide, I'm taking one example. The example is orthohydroxybenzophenone. So this on ground state one, this on photoreduction, this on irradiation, it will give you singlet, and this singlet crosses the intersystem crossing and forming a triplet one. So triplet one loses the proton, forming a resonance param. The obtained resonance param is of more of enal param. So that's the reason in polar solvent, hydroxy benzophenone suppresses the photo reduction. So in non-polar param 1, this is the param 1. Param 1 means a ketonic param will be the more stable one. That's the reason you can remember that non-polar solvents favors the photoreduction and polar solvent suppress the photoreduction. That's what you need to remember. I will go to the next slide. Okay. So here, I'm taking one question. Para-aminobenzophenone, even in polar solvents, readily undergo photoreduction. Explain. So this is because you know that in HCl, it converts the amino group into ammonium salt. So what it means? It means that the electron donating nature of the amine is removed. Then what will happen? The carbonyl nature is retained. So in such case, it favors the photoreduction. So you can remember that para-amino benzophenone undergoes photoreduction in presence of HCl. Why? Because HCl converts the amino group into ammonium chloride. Thereby, carbonyl nature of the benzophenone retained. That's the reason it undergoes photo reduction. I will go to the next slide. So here I'm taking the para-methoxybenzophenone. So this para-methoxybenzophenone, when you are comparing with the hydroxybenzophenone. Hydroxybenzophenone resonance param 2 will be the stable. Resonance param 2 means it's a enal param 1. In para-methoxybenzene, there is no such params, means resonance param 2 is not favored. That means resonance param 1 is favored. That means para-methoxybenzophenone, phenoxyanion is not param. It retains the carbonyl nature. That's the reason photoreduction is favored. So this is about the few example of photoreduction. And let's look into the intramolecular photo sensitization. Here I'm taking a general example. A is the acceptor, D will be the donor. at ground state. What it means? It means that if there is a compound contains an acceptor and donor in a molecule, when such molecules are irradiated, the donor one gets converted into singlet, and singlet donor crosses the intersystem crossing and forming a triplet of the donor. Since the donor contains the acceptor within a molecule, it transfers the energy to the acceptor. In such cases, photosensitization success rate is less. It's because of the molecule itself is contains a acceptor in it. So now, if the energy transferred donor to the acceptor gets converted into triplet. Overall, we can remember that intramolecular photosensitization means a molecule which contains donor as well as the acceptor. Donor on irradiation gets converted into singlet. Later, it crosses the intersystem crossing and then forms a triplet. And now the triplet donor transfer its energy to the acceptor. Acceptor is present within the molecule. Now the acceptor gets a triplet one and donor gets ground state one. I will go to the next slide. Here I am taking an example. This moiety, this is completely one moiety, but it contains acceptor as well as the donor one. Both are in ground state. So on irradiation of the carbonyl lambda max, carbonyl compound undergoes singlet state. And this crosses the intersystem crossing, forming a triplet one. Now transfer its donor excited extra energy to the acceptor one. Acceptor gets triplet and donor gets 0. This is what the intramolecular photosensitization. So in place of this moiety, we can also take a naphthalene containing one and also a tetraline or derivatives of the naphthalene can act as a acceptor and benzophenone will act as a donor. Overall, these compounds photoreductions highly difficult due to intramolecular photosensitization. So with this, I will go to the next slide. In the next slide, I am taking one more example. Is ground state one irradiated of the carbonyl lambda max gets converted into singlet, and before obstructing the proton, donor transfer its energy to the acceptor. So because of this problem, intramolecular molecules containing acceptor in it is difficult for photoreduction product. With this, I will go to the next slide. In the next slide, to get a success or to make the carbonyl compound, more particularly those compounds containing acceptor in it, we need to follow certain conditions. What are those conditions? By using highly efficient hydrogen radical donor, that means tributyl tin hydride. If we are using tributyl tin hydride for the hydrogen source, then photoreduction can be achieved with the electron acceptor containing carbonyl compound. One more condition, by doing the reaction at high temperature, then photoreduction can be achieved. By using nonpolar solvent, photoreduction can be achieved. So now onwards, we will look into the few examples of photoreduction. This is one carbonyl compound, naphthaldehyde. This is also a naphthaldehyde. One naphthaldehyde, two naphthaldehyde, and benzophenone, more particularly a dye product, because benzophenone substituted, amino containing substituted will act as a dye. So here I am taking an example, so a benzophenone and a diethylamine. So the diethyl aniline will act as a hydrogen source. Benzophenone will act as a photosensitizer. So when irradiated with the carbonyl lambda max, the products are phenol and then a dimer of N-phenyl methyl N-phenyl methyl amine dimer will be the product. Let's look into this mechanism of this reaction. Here, carbonyl compound react with the diethyl aniline. On irradiation, use phenol and dimer product. Let's look into the mechanism. So this is the mechanism. The lone pair present on the nitrogen, one electron will be moved from here to here. So thereby O minus and the radical is formed. And this O minus picks up the proton from the one of the CH3 of the aniline. Then the obtained one is a radical here. And then one more benzohydral radical is forming. This benzohydral radical can undergo dimerization, forming a phenol, and this one undergo this pi bond undergo homolytic cleavage, forming a radical here. This radical react with the taking a pointer. Okay. Okay. Then I'll take a pointer. Right. So this radical undergoes dimerization, forming a dimer product. With this, I'm taking here one more example. A benzophenone react with the toluene. Okay. Toluene will act as a proton source. Then the products are phenol, benzohydral, and then substituted toluene substituted benzohydral. Similarly, if it's a mechanism. Key intermediates are benzohydral radical and toluene radical. Suppose if you are taking a carbonyl compound of fullerene ketone, then a diethyl aniline can be used as a hydrogen source. Then the product is a phenol, more particularly of this kind. Okay, here I am taking a, that anthraquinone, more particularly 1,2-anthraquinone. This is 1,2-anthraquinone. Anthraquinone is a carbonyl compound. If it is react with in presence of toluene and irradiated, it is found that this carbonyl react with the toluene, forming a product like this. And this carbonyl also react with the toluene, forming in this kind of. These two products are the formed. What it means? It means that only one of the carbonyl group is reduced, not the two carbonyl groups. Then here is the mechanism. Carbonyl compound, that means one of the carbonyl pi electron of the carbonyl compound undergoes homolytic cleavage, forming a obstruct the proton from the toluene, forming an intermediate, and this intermediate radical react with this radical, forming a product, neutral product. Similarly, this kind of moiety are formed. So with this, I will go to the next slide. Here, a pinacol 1, if it is treated with the quinone, okay, 1,4 quinone, it is nothing but a reduction, that means glycolic bond cleavage, oxidation. So the quinone undergoes reduction, alcohol undergoes oxidation. So the glycolic bond, this bond is cleaved, forming two molecular benzophenone. That means reverse of photoreduction. Reverse of photoreduction is possible when it is treated with quinone. How it is formed? This is the mechanism. That means cleavage here, cleavage here. Okay. It means that here there is a bond formation, and how the 1,4 phenol is formed, and two carbonyl compounds are formed. So here I'm taking few more examples. Tetralone, name of this compound is tetralone, treated with the isopropanol. When it is irradiated, a product is obtained like this. So suppose a bicyclic compound having two carbonyl compound, if it is treated with the alcohol in presence of light, one of the hydroxy groups only reduced. This carbonyl group is reduced, or this carbonyl group will be reduced. Obtained product is a mixture. With this, I will go to the next slide. In the next slide, I'm taking intramolecular photoreduction. Intramolecular photoreduction means it contains more particularly alpha, beta, gamma, delta, explanon. Okay. In this case, explanon hydrogen is captured, forming a bicyclic compound. We have the bicyclic compound having ring junctions cis and trans. So cis one will be the major product compared to the trans one. So here I am taking a carbonyl compound. You have to identify carbonyl compound and the hydrogen. So this is the carbonyl compound, means alpha, beta, gamma, delta. Delta hydrogen is cleaved, forming a photoreduction product. That means there will be a new bond formation between this carbon and this carbon. CO is converted into OH. Similarly, between these two carbon. Similarly, between these two, this is a key intermediate forming a product. So here I'm taking one more example. This is the benzylic carbon atom. Of course, it contains a hydrogen, alpha, beta, gamma, delta. Delta hydrogen obstruction, forming conversion of this CO into OH. And this is again a key intermediate converted into, that means polycyclic moiety is also converted into cyclic moiety. That means new bond formation between this carbon and this carbon. Similarly, new bond formation between this carbon and this carbon, forming a cyclic ethers. Okay. So cyclo additions. Paterno Buchi reaction. So it's one name reaction, and it is important. Few questions you can expect in the main examination. So what is the Paterno-Buchi reaction? It's nothing but a reaction of 2 pi plus 2 pi cycloadditions. 2 pi plus 2 pi. That means this is one 2 pi, this is another 2 pi. 2 pi cycloaddition forming a oxetane moiety. That means 2 pi cycloaddition between the carbonyl compounds and olefins or alkynes is called Paterno reaction. So in place of alkene, one can also take alkyne also. So if the alkyne is the product, then alkyne is the reactant, then alpha beta unsaturated the product will be alpha beta unsaturated carbonyl compounds are the product. That means Paterno-Buchi reactions can be carried out. It's nothing but a 2 plus 2 cycloaddition, more particularly between the carbonyl compound and olefins or alkynes is called Paterno-Buchi reaction. So here, any carbonyl compound react with olefin or on irradiation gives oxetane. Oxetane means 4-membered ring with the oxygen as the product. Carbonyl compound react with the alkyne gives rise to oxetane. So here I am taking a benzophenone and then unsymmetrical ketone. Unsymmetrical ketone means it is possible to extract the two products. Out of two, this will be the major product. And here there will be a regio selectivity. Similarly, this is also a unsymmetrical ketone. Unsymmetrical ketone, unsymmetrical alkene react with the carbonyl compound, forms two oxetane moiety. This one will be the major one compared to this one. Highly alkylated carbon of the olefin converted to a carbonyl carbon in the formation of major product. Okay, what are the characteristics of the paterno-Buchi reaction? Reaction mixture irradiated at absorption wavelength, lambda max of the carbonyl compound. Reaction excited states are N2 pi star and N2 pi star. This is singlet and this is triplet. N2 pi star singlet paterno-Buchi reactions are stereoselective. N2 pi star triplet or paterno-Buchi reactions are non-stereospecific. At the time of addition, carbonyl carbon at excited state and alkyne or olefin at the ground state. Reaction intermediates are 1,4 diradicals. Before the formation of 1,4 biradical intermediate, excited state of the carbonyl compound forms temporarily unstable complex with the ground state olefins called exciplex, change charge transfer complex. If alkane is unsymmetrical, the reaction proceeds in such a way to produce stable radical intermediate mixture of product obtained in unequal ratio called regioselectivity. Alkanes, paterno-Buchi products are oxetane or alkynes, or paterno-Buchi products are oxetanes. Okay, I will go to the next slide. Again, struck is there. Slides are not moving. I will stop sharing and again I will share the screen. Okay. Now also slides are not moving. When I will, again I will stop sharing. Okay. Now it's moving. Right. So previous slide is this. Right now. So here I'm taking an example, more particularly paterno-Buchi reaction. A carbonyl compound react with the alkene. And here the lambda max is the benzophenone lambda max. That means both the reactants are irradiated for the lambda max of the carbonyl compound. So two products are obtained. This is the one and this is one more. And this will be the major one compared to this one. And here, mechanism, carbonyl compounds ground state, when it is irradiated with the lambda max of the benzophenone, it will go to the singlet one, and singlet one crosses, intersystem crossing, forming a triplet one. So this triplet one, triplet of the benzophenone react with the ground state alkene, forming a intermediate like this. That means there will be a new bond formation between this carbonyl carbon and the more substituted carbon. And it is also learned that initially there will be a key intermediate. One more key intermediate is the bond formation between the oxygen and the carbon. Oxygen-carbon bond formation will be the key intermediate. And this later on carbon-carbon bond formation. So this is how the major product is formed. I will repeat. So mechanism, if it is related to the mechanism of paterno-Buchi reaction, the carbonyl compounds are irradiated at the lambda max of the carbonyl compound, and carbonyl compounds converted into singlet, and singlet crosses the intersystem crossing, forming a triplet one. Triplet of the carbonyl compound react with the alkene of ground state alkene, forming a key intermediate. In that key intermediate, what is the important thing? The first bond formation is between the oxygen and the carbon. Later bond formation between the carbon and carbon. So this is how a major product oxetane is obtained in paterno-Buchi reaction. I will go to the next slide. It's again, slides are not moving. Most probably, I need to share it again. Okay. Right. So now also it's not moving. I will stop sharing. Okay. I will use other one. Yes. Right. Okay. So here, this is how the byproduct is formed. The byproduct also a unstable species. Why it is unstable? Because it's a primary carbon. So that's the reason it is unstable. Primary free radical. And of course, this radical is stable. This is not the stable. That's the reason the product is minor. So what are the few points you have to remember in paterno-Buchi reaction? If olefin is electron rich, 1,4 biradical formation, oxygen carbon bond first takes place. It is common in majority of the paterno-Buchi reaction. If olefin is electron deficient, then carbon-carbon bond formation takes place first. So let's look into the few examples. And here is the one example. A carbonyl compound react with the olefin. What is olefin here? Dicyanoalkene is the olefin, and the product is this one. And you can observe that there is a retention of configuration. That means cyano groups are in the same side. So if we are looking at the mechanism, Here, a ground state benzophenone on irradiation with the lambda max of the benzophenone, it's converted into singlet. This crosses the intersystem crossing, forming a triplet. This triplet state of the carbonyl compound react with the ground state of the alkene, forming a product. What is that product? You know that this alkene is the electron with the triangle. That's the reason carbon-carbon bond formation takes place first. Later on, oxygen-carbon takes place, forming a major product. I will go to the next slide. In the next slide here, we are talking about the electron-rich olefin and oxygen-carbon bond formation that takes place. Suppose electron deficient one, then carbon-carbon bond takes place first. Whenever the olefin is electron rich, transfer of electrons from olefin to n orbital of the carbon oxygen. As a result, formation of OC bond. I will go to the next slide. Right. So here, stereochemistry we are talking. Stereochemistry means N2 pi star paterno-Buchi reactions are specific, means stereo-specific. Example, aliphatic carbonyl compounds such as acetone and acetaldehyde. So compared to aromatic carbonyl compound, aliphatic carbonyl compounds are inefficient at intersystem crossing. So that means N2 pi star singlet excited states paterno-Buchi reactions. In paterno-Buchi reaction, if all the products retain stereochemistry of the ground state olefin called stereospecific paterno-Buchi reaction. That is N2 pi star reactions are stereospecific. Here I am taking acetone. It's a aliphatic carbonyl compound. When it is treated with butadiene, it is possible to get a different product. What are the different products? Cis product. This is also a cis product. Retention of configuration. Then suppose retention of configuration with respect to alkene, because alkene is the cis one. That's the reason. And suppose if I am taking a trans, here also trans is there. Okay, this is also a trans, this is also a trans one. So overall, you can remember that stereochemistry is retained with respect to the alkene. I will go to the next one. Here I am taking one more example. If stereospecific reactions products form cis or trans olefins are different. So that means acetaldehyde I am taking. Acetaldehyde, when it is react with the ground state cis butene, when it is irradiated with the lambda max of the acetaldehyde, forming these two products, cis and trans. So here, with respect to the alkene, it is no, actually both are cis only. Okay, this is not the trans. This is also a cis, but cis and trans with respect to the alkene. Here also cis is there, means both the substituents are towards the observer, and here both the substituents are away from the observer. But when you are looking at the substituent present on here, then between this and this, it is a trans one. Between these two groups and this group, then it is a cis one. So here the products are diastereomers. So suppose a carbonyl compound, when it is react with the trans butene, then trans and cis products are the obtained one. So here what you can observe, trans between this substituent and this substituent is trans, between this substituent and this substituents are trans. So this cis and trans in a cyclic substituted products. It is not related to the double bond or geometrical isomerism, but it is related to the cyclic substituted molecules. Right. This is about Maybe what I will do, I will stop at this stage and I will continue in the next class. Next means soon I will share one more link, maybe in the afternoon or otherwise after 1 hour. I will share one more link. I will continue in that class. I will end now.